Hello, everyone, and welcome to iTelescope again, another Friday. It's been some time. My name is Christian Sasser. I'm the astronomer in charge, and I'm really delighted today to introduce to you Lucie Rowland. Lucie Rowland is originally from London, then she went to Durham University and then to Leiden University. So she's been dealing with nearby galaxies, dwarf galaxies, and now she's going very far back in the university too. She's gone to Holland, universe and universities, both right. And she's a first-year student, and the topic, of course, is so incredibly interesting. She's an experimentalist, which has really done my heart because I'm also an experimentalist. So, Lucie, it's all over to you. How are you?
Good, thank you, and thank you for inviting me here, and thank you for the introduction. It's very nice. So I will share my screen and get started.
Okay, that's good.
So I'm hoping everyone can see my screen okay?
Yes, we can.
Thank you. So yeah, so as Christian already said, my name is Lucie Rowland and I'm a PhD student at Leiden Observatory. And my research and my work focuses on massive galaxies in the early universe. And so also, as Christian said, I'm not originally from Leiden. I'm originally from London. And then I moved up to Durham, which is a beautiful city in the north of England, to do my undergraduate and master's in physics and astronomy. And then I graduated from Durham really just last summer. And only a few weeks later, I moved over to Leiden to start my PhD. And so Leiden is this very, very beautiful town just outside of Amsterdam, and it's got a very, very rich history in physics and astronomy. So on the left here is an image of our old observatory, and so this is actually the oldest working university observatory in the world. So it's not used so much for scientific purposes anymore, but it's still used for lots of educational and public outreach activities, which is really exciting. And we also have a lot of notable alumni, so people like Albert Einstein, Jan Oort, even some connections to Galileo. And what was quite funny, I don't know if any of you have had the chance to watch the Oppenheimer movie yet. I saw it just last night. And what was quite funny was there was a scene, I won't give any spoilers, but there's a scene where Oppenheimer himself and lots of other key physicists go to visit Leiden. So Leiden has always held lots of, big physics meetings. And for a funny bit of trivia, there's a point at which some characters are meant to be speaking in Dutch, but according to my Dutch-speaking friends, they're just speaking in gibberish. But regardless of that language issue, it's still a very, very brilliant movie, and I really recommend it. So since starting my PhD here at Leiden, I've had also the opportunity to become an author for Astrobytes. I'm going to minimize this. There you go. So as an author for Astrobytes, this is a website that's run by PhD students and postdoc students. And what we try to do is we take sort of the latest astrophysics research papers and we try to kind of summarize them in a way that's more accessible and digestible for specifically for undergraduates, but also we want to make them more accessible for kind of everyone with an interest in astronomy. And so this is something that I'm very passionate about and looking forward to doing more of in the future. So Astrobytes advertisement aside, I'm going to talk to you mainly about my sort of big picture research question. So that is to try and investigate and characterize massive star-forming galaxies at high redshift with ALMA and JWST. So I am predominantly an observational astrophysicist. That means I don't really work with, with supercomputers or anything like that. I mainly work on, real telescope data, and I try to bridge what we see with what theory predicts. And I mostly work with as I said, these ALMA and JWST telescopes, where ALMA is arguably the most powerful ground-based telescope, and JWST is, of course, this super powerful, shiny new space-based telescope. So I'm very fortunate, both since my team have access to both of these amazing telescopes and some of their data, but also because I had a really, I have very lucky timing. I started my PhD just as JWST started taking its first observations. So I had really the perfect timing to get into a PhD in astrophysics. So I realized my big title has a lot of terms in there. I'm hoping this doesn't ruin what you guys can see. If you can see the little zoom window in the corner, I'll maybe keep that minimized. But yeah, so I realized there are a lot of terms to unpack in this title, so I'm going to try and go through them bit by bit. Starting with, why exactly are we interested specifically in massive galaxies? What's all the fuss about massive galaxies? And so for a bit of context, the Milky Way is probably what we would consider to be a normal sized galaxy. And already it's about 10 to the 42 kilograms. So that's 10 and then 42 zeros kilograms in mass. So that's already huge. That's about 1 trillion times the mass of the sun. But what I'm really interested in is in the galaxies that are very massive at their point in time and space. So for the local universe, that's about 100 to 1,000 times bigger than the Milky Way. And the reason that they're so interesting is because they're very useful to try and study how galaxies evolve. So we know that as galaxies evolve over time, they tend to get bigger and bigger because they're forming more and more stars, they're accreting more and more gas, and they also sort of collide and merge with each other. So they get more and more massive over time. So studying the most massive galaxies gives us a glimpse or some insight into the more extreme sides of galaxy evolution. And also as things get bigger, we tend to get kind of more extreme physics. So the gravitational force within these massive galaxies is going to be incredibly huge, which has lots of interesting effects, both on the galaxies themselves, but also on their surroundings. And galaxies can even become sufficiently massive to host these sort of supermassive black holes at their center. And this causes these galaxies to become very, very active. And that has a lot of interesting effects and makes them very, very extreme environments. And for a more kind of technical reason, the more massive galaxies get, makes sense, the more stars they tend to have, and that makes them brighter and a lot easier to detect. So for example, if we were to observe a massive galaxy for say 10 minutes, we get quite a lot of information about that galaxy. But if we were to observe another smaller and so fainter galaxy, it would probably take hours to get that same amount of information, that same amount of detail. Okay, so then the sort of next keyword is star forming. So why are we interested in star forming galaxies and what are they? Well, so first in the sort of basic picture of star formation, we know that stars form in clouds of gas and dust. And a great example in our local universe, in our own galaxy, is the Orion Nebula, which is this really, really beautiful star forming region that there have been so many pictures taken of it. And so massive star-forming galaxies will typically have lots and lots of those sorts of star-forming clouds. So for example, NGC 300, a local massive galaxy, every one of these kind of purple bubbles that you can see in this image, especially along its kind of spiral arms, those are individual star-forming clouds where lots and lots of stars are being formed. But so over time, those star-forming clouds eventually run out of fuel and star formation stops. And so then we get these, by comparison, much kind of duller and what we call dead galaxies, where they're mainly just made up of the kind of smaller, longer living stars. So an example would be M87. So in general, star-forming galaxies they are much brighter and they're much more colourful, and we can learn a lot more about star formation. And one of the great tools to learn about star formation from star-forming galaxies are these, what we call bright emission lines. So when you extract a spectrum of a galaxy, so here we've got on the y-axis is the flux or the amount of light for every wavelength or colour. That's basically what we get, what we mean by the spectrum of a galaxy. And then what we also get is the continuum, which is kind of the baseline, so this very faint, very bottom line. So obviously what we first see is these emission lines are so bright that they really overshadow this kind of continuum line. So we get a lot more information from these bright emission lines, and they're a lot easier to detect. On the flip side, if we were to look at, these more dead galaxies that are no longer forming stars, we only really get this continuum. So this is kind of, imagine if you really just zoomed in to the sort of low baseline here and there weren't any emission lines. That's kind of what this is showing. So we lose all the information that's encoded in those really, really bright spikes of flux. So really we need to observe these star-forming galaxies to really understand what's going on with star formation. And also do keep in mind bright emission lines, because I'm going to go back to that idea later on in the talk. And so now we're going to move on to high redshift. So I'm hoping that some of you already have some understanding of what I mean by high redshift, but I'll give a quick summary. So the basic thing to remember is that high redshift is very synonymous with being very distant and being in the early universe. So it's used as a measure of both distance and time, which can sound quite confusing, but it does make sense if you remember that the universe is expanding. And so what that means is the space between galaxies is expanding. So galaxies are moving farther and farther away from each other and farther away from us. So if we were to observe a galaxy moving away from us, like in this sort of top animation, as it moves away, its light gets stretched, its wavelength increases, and it appears to be redder and redder. And so the further away a galaxy is, because space is expanding, that means that it's moving away from us faster and faster. And so it becomes redder and redder at higher distances. And also because light takes time to travel to us, looking at high redshift basically means that we are looking back in time. So what's quite interesting is that the exact definition of high redshift, or just how far back you have to look for it to be considered high redshift, is quite a subjective topic amongst astronomers, especially now, now that we have JWST. So depending on what kind of astronomer you ask, chances are the answer you get is going to be slightly different. And typically, because the high redshift universe is a really exciting field to be in, typically astronomers will give an answer that's slightly below the redshift they're looking at, so that we look like we're all studying high redshift. But I'm curious to see for you guys what you would already maybe consider to be something that's high redshift. So from a scale of 0, which is the Milky Way, so that's kind of the present day and all the local group galaxies that are at redshift 0, all the way up to the Big Bang, which is at redshift infinity. So that's kind of the outer edge of our universe. So what do you think in your mind would be considered as high redshift? And so to answer this question, what we're going to use is this website called wooclap.com. So there's a couple of different ways you guys can do this. You can either scan the QR code, which should take you directly to this event, or you can go to this website, wooclap.com, and enter in our event code, and that should take you to the event. So I'll wait a couple of minutes for people to do that. I can see that we've got some participants already joining. You can do this on your phone, on your tablet, on your laptop, wherever you like. So I'll wait another couple of minutes. And we're going to use this again throughout the talk. So don't, close the browser after we finish this first question. So I'll wait a couple more minutes. And if anyone's having any issues to access it, maybe you can put something on the chat and I'll see if I can see where the messages are.
Yeah, so don't forget to, you got the event code, right? Which you need to put in, right?
Yes. So the event code is CGPEKT. I'll leave that up for another few seconds. So again, the event code is CGPEKT. Okay, hoping everyone who wants to answer the question has gone on to there, and I'll display the first. Okay, a couple of more have just joined. Okay, well, I'll start the first question on the website. Okay, so the first question is how would you define high redshift? And I'm hoping this will kind of put what we mean by redshift into a bit of context. So I'm not going to tell you what redshift I work at just yet, but I will say that almost everyone, apart from kind of theoretical cosmologists, would probably say that what I work at is at high redshift. So don't be worried about insulting me. And also as a hint, redshift is not a linear scale. So the difference between redshift 0 and redshift 0.5 is probably around 4 billion years. But the difference between like redshift 100 and redshift infinity is only around like 10 million years, which in like astronomical terms, that's not very long at all. So I'll give people a few more minutes, or a few more seconds rather, to try and answer this. So there is no right or wrong answer. This is just, I want your opinion on what you would consider to be high redshift. I can maybe, in a minute, I'll show what people have voted for, but I'll give you guys another little bit of time. And I thought it would be quite nice to kind of put it into context of kind of key points in what we know about the history of the universe. So even just between redshift 0 and 0.0001, that's kind of our entire time as humans on Earth.
I hope you're managing with this new tool. It works nice, but it gets a bit, you have to get a bit used to it. So hopefully you can see the questions.
Yes, I will maybe put the poll up now. Can you see the poll here?
Yep.
I hope that might influence what people are saying, but interestingly, so I'm interested. So it seems people are saying more kind of these values down here. So I will now say that I work typically at redshift greater than 6. And so like I said before, most astronomers would consider that to be high redshift. I think only really my more theoretical cosmologist friends would say something like this, and that's because they are really only interested in the first few seconds after the Big Bang, and so that's at redshift like 1,000, a million, or something like this. But if I was asked this question, I would probably maybe go with one of these two, but maybe I am just biased because I am at redshift 6 or so. But yeah, that was interesting. Okay, I think I can see the results like this. I've stopped the poll now, and I will go back to the presentation. So like I said, I work at sort of redshift of around 6 to 12, and that's what's known as the re-ionization era. So that's illustrates where we are in the history or the timeline of the universe. So the re-ionization era is a very, very important time in cosmic history. So it starts about up to about 1 billion years after the Big Bang. And it starts sort of at the end of the cosmic dark ages. So this is when sort of the first stars and galaxies in the universe switch on. And what they do is those very first stars, they emit radiation and light, and they ionize their surroundings. So prior to the reionization era, the universe is mainly sort of neutral hydrogen gas. And then after the reionization era, the universe is a lot more like what we kind of see in our universe today, where it's mainly lots of ionized gas. And also within this epoch, those first galaxies really do evolve considerably. So they merge and collide and interact and form more and more stars and grow more and more massive. So next I'm going to move on to how I'm able to study these galaxies. And so the first telescope I use is ALMA. So ALMA is an interferometer telescope located in the Atacama Desert, and it's made up of lots of these dishes, and it's quite funny. So what happens is, to observe a particular object at a particular wavelength, what they basically have to do is kind of drive these dishes around, which is quite funny. And so the sort of wavelength range that ALMA operates at is around 0.32 to 3.6 millimeters. So in high redshift language, that basically means that we can study really only their cold gas and their dust content. So it's important to note that no one telescope can tell you everything there is to know about a galaxy. What you learn is very, very much dependent on the wavelength that your telescope or your instrument has access to. So specifically for ALMA, we get the cold gas and the dust content, and some of the cold gas kinematics also. So finally, I'm going to move on to JWST. So I've already said that higher redshift galaxies appear redder and redder, and that's because a lot of their light gets shifted into the infrared. So unfortunately, well, kind of unfortunately at least, the Earth's atmosphere is really, really good at absorbing infrared light. And I said kind of unfortunately because it's this property, this capability of our atmosphere at absorbing infrared light, that's what essentially stops the sun from killing us and killing life on the planet. But it is a bit of a pain for astronomers because a lot of really useful information is found in the infrared wavelength range. So people, or astronomers rather, have tried various different solutions to try and solve this. One of my favorite solutions was we put a telescope on a plane and called it Sophia. But unfortunately, Sophia has now been grounded. I think it stopped going on flights and stopped taking observations sometime last year, unfortunately. But what we really needed was a really big space-based infrared telescope. And so that's exactly where JWST comes in. So JWST operates in the near to mid infrared. and it's just incredibly powerful. And what that means is that we can get really, really faint light from some of the earliest galaxies in the universe. And this was one of the very, very big aims of JWST. So like I said before, what you learn about a galaxy very much depends on the wavelength that your telescope operates at. And so with ALMA, we got information on the cold gas and on the dust, but then now with JWST, we can get all this information on the warm ionized gas, on the populations of stars within the galaxies, and also on the star-forming regions within those galaxies. So with those two powerful telescopes combined, we really have access to a real treasure chest of information about high redshift or reionization era galaxies. So in theory, what were we expecting? What did we know or think we know before JWST? And so one very important idea was this theory called hierarchical structure formation theory. And in essence, what this kind of states is that the smallest structures at the very beginning of the universe collided and merged together to form larger and larger structures until eventually we get to massive galaxies. So this is a very, very important sort of basic theory behind galaxy evolution. And so if you wind back the clock, what do we expect to see? Well, first, we expect to see high redshift galaxies to be smaller than more local galaxies. And we also expect there to be more interactions and more mergers at high redshift, and that kind of creates all sorts of chaotic collisions. And also because these galaxies at high redshift are younger, they've had less time to evolve. And so that should also mean that they have had less time to enrich their gas with metals. And metals are what stars emit out to their surroundings rather, sort of over time. It takes quite a long time to really enrich their surroundings with heavy elements. So that all leads to this kind of big idea that most galaxies at high redshift should be small, and they should be less evolved, and they should look quite chaotic. But I've talked a lot about massive galaxies. I don't really study the kind of the common small high redshift galaxies that obey this. I really want to focus on the more massive ones, the ones that challenge this whole picture. And they do exist, they're not impossible, but at least before JWST, they were incredibly rare. There was only really a handful of them that existed. And the kind of one of the largest handfuls that we had was collected by the Rebels team, which I am now part of. So the principal investigator, my supervisor, Richard Bowens, he was heavily influenced, of course, by Star Wars when he picked both the logo and the title for this big team. But this isn't just an empty title that he made up for a bit of fun. It does actually stand for something. So we're going to have another online question where I want you to try and guess what Rebels stands for. So I've given you the final word, the last word for free. It's survey, and then I would like you guys to try and guess what the previous words are. So again, if you need to go back to the website, you can use the QR code or go to wooclap.com and enter in our event code. But try to guess maybe what it stands for. And I've given clues in previous slides, but I'm happy to give more clues if it looks like people are struggling. But it's very much linked into what I was saying in some previous slides. So I'll give you guys a couple of minutes to try and guess that. And if people are struggling, I will give some clues. I'm just going to check this message in the chat. I might answer these questions at the end, maybe.
Yeah, I haven't played enough Scrabble, I'm sure. That's a problem.
Okay, so I can give a clue. So I think it numbers the words 1 to 5. That doesn't mean how many letters are within each word, but I'll give you a clue. The second word is era, spelled E-R-A. And the final word, the word beginning with L, is line, so L-I-N-E. So you should have heard those words before. This is maybe a test of how well people have been paying attention. So era and line are the E word and the L word. Someone's got the right answer, so it's not impossible to guess this. Give another minute or so. So again, the second word is era and the last word is line. It's quite fun seeing the guesses. I won't put up people's guesses, don't worry. Don't feel worried that everyone might see them, but I will just show the correct answer in another few seconds. Yep, quite a few people are getting it correct. Okay, I'm going to give you 20 more seconds. Okay. How do I stop? Okay, so the correct answer is the re-ionization era bright emission line survey. So it does, it can sound quite complicated, but it's as I was saying before. So we're focusing on the re-ionization era, so that redshift range around 6 to 12, and we're focusing on bright emission lines, and those are very characteristic of massive star-forming galaxies. So kind of a combination of the previous slides. So it's the re-ionization era bright emission line survey. And so this Rebels program was awarded to become an ALMA large program. And so what that essentially means is we were given lots and lots of ALMA time to observe our targets, so around 70 hours. And the team targeted 40 bright objects predicted to be at around redshift 6 to 8. That's about 1 billion to 600 million years after the Big Bang. And what we were able to do is we were able to confirm these redshifts for almost all of the targets. And simultaneously, we got information on the dust content and the C+ emission, where the C+ emission is basically a very bright emission line that tells us information about the cold gas predominantly within these galaxies. So here you can see some of our significant detections where the cold gas is the sort of blue contours and the dust content is the orange contours. So we get information both on kind of the spatial distribution of the cold gas and the dust, but also we get information on how much of those components there are and some information about their properties. And so what's really, really exciting, as well as all the ALMA data we've got, we also are about to, or in the process of, getting JWST data. So these observations could happen anytime within the next year or so. We've already had 2 observed, and they could be taking some of our data right now as we speak, who knows. And so what this really means is that we're going to get a really full picture of what's going on within these 12 massive galaxies, because we're going to have the information from ALMA on the cold gas and the dust, and then all the exciting new high quality information from JWST on almost everything else. So things like the warm ionized gas, the star forming regions, and the stellar populations within these galaxies. So I'm going to go back to some more details about this data in a little bit, but I first want to talk about JWST in general and how we're finding high redshift galaxies and investigating their properties with JWST. And I'm going to start with a clip of the launch because I like watching it. So I'm going to skip ahead slightly.
30 seconds and counting.
Around here. Hopefully this is working for you all.
6, 5, 4, 3, 2, unité, stop. And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight.
So I'll stop it there. I hope both the video and the sound work for you guys, but I quite like the sort of the caption they give it of JWST shooting off back to the early universe. So I remember watching this. So this was on Christmas Day back in 2021, and I was at home for the Christmas holidays, but I was still finishing up my master's. And at that point, I had already applied to Leiden to do my PhD. And I had specifically applied to this Rebels project that I'm now on because I knew it would be very much focused on high redshift JWST data. And so I was very, very excited, but also very nervous to watch the launch because I knew that if anything went wrong, this PhD project I'm now working on and pretty much all the other ones I had applied to would basically blow up alongside the telescope. So I was very nervous, but also very excited. But thankfully it all went well, and JWST has been doing amazingly well, and it's performed even better than we expected. And so in particular, oops, playing again. In particular, we really wanted JWST to find high redshift galaxies, and it has definitely done so. It's found lots and lots. So we're going to have another quick question. So for any JWST fans out there, back last summer, JWST released 5 early science images, and this image on the left here was one of them. So I'm going to see if anyone can remember the name. It's going to be a multiple choice question, so I don't expect you to remember it on the top of your head. But if you go back to our sort of interactive woo clap, and we're going to try and guess the name of this image. So I wonder if I can still see who's there. So these are your options. So there were 5 images released in total, and this was one of them. So for anyone who maybe remembers the name or can sort of figure it out, maybe have a go at guessing what the name of this image was. People answering this one faster, which is interesting.
Yeah, those images will know what the Carina Nebula looks like, because we actually took that in one of the webinars. We took the Carina Nebula from the James Webb or the JWST, and we superimposed it with one of ours. So it was very nice.
Okay, so you guys could definitely know.
So it's definitely not this one.
Nebula looks like,
I can give you that hint. Yeah.
Okay, I'll give 30 more seconds. And then I'm going to show each of the images because they are just so beautiful. It's nice to look at them.
Yep.
Okay, I'm going to stop it there and I'm going to show you the images. So the first image, the Carina Nebula, this is a very beautiful star-forming region, local star-forming region. This is the JWST image of the Carina Nebula. And then this is the second image. This is Stephan's quintet. So this is a group of local interacting galaxies that will eventually merge together. And then this is the JWST image of the Southern Ring Nebula, both with the near-infrared and the mid-infrared capabilities. And this is a planetary nebula, so kind of what's left over after a star dies. And then this is WASP-79b, which got quite a few votes. And this was a spectrum rather than an image. So it's a spectrum from an exoplanet atmosphere where we saw some water signatures. So then finally, the correct answer for this question, this image I showed here, is actually called SMACS 0723. So it's not a very interesting name, but what SMACS 0723 essentially is it's this bright cluster of galaxies in the middle. So these are sort of more local massive galaxies that are acting as a lens and magnifying all the distant galaxies behind it. So that's where you get these weird sort of tail-like features, because it's acting as a very strong gravitational lens. So within this image alone, lots of high redshift galaxies were found. This was kind of the deepest infrared image taken at that point, and we found lots of high redshift galaxies. So we're going to do another quick question, and I'm going to try and get you guys to see if you can spot any high redshift galaxies. I'm not going to ask you to do it on the image as a whole, because that would just be really, really difficult. I'm going to zoom in a little bit and see if we can find some of the high redshift galaxies based on what I've kind of already told you about high redshift galaxies. So remember that they're small, they're red, and that should give you some hints to see if you can try and find some. So this is the first one, the first image. So this is a zoom in of that SMACS 0723 image. So see if you can spot where the high redshift galaxy may be. I think all you need to do is click on the image. So see if you can have a go. And so again, remember that we anticipate high redshift galaxies. They're very, very far away, so they're going to look very, very small, and their light's going to be very, very much redshifted.
I think it's absolutely cool that you can actually click on the image. I've not seen that before. I really like that, you know.
Yeah, this website is very useful. So we've had a few correct answers, but I'm going to leave it up for a little bit longer. There's also a bit of a clue in the slide. I'm going to maybe show some of the guesses again, maybe. Oops. Okay, no, I'm not going to leave the presentation. So this is the correct answer. It's this tiny little thing here. So it is quite hard to spot, so I won't judge that you maybe picked something else, but this is the highest redshift, at least in this portion of this image. So this is at about redshift 8.5, so that's about 13.2 billion years ago. And so it's very characteristic, if you will, of what we kind of often see of high redshift galaxies in these sorts of images. It's very small and it's very red. So we're going to try the game again with another image. So we're going to try it with this image now. So this is slightly more zoomed out, so there's more objects to choose from, but hopefully you can remember how the last one looked and what was so characteristic about it that you can have another go. And again, there's a clue sort of in the slide. Yeah, we've got some right answers. So again, pretty much every point of light in the SMACS 0723 and in this zoomed in version of it is going to be a galaxy, which is just incredible because there were just, I think in the catalogue initially when they tried to search for all the sources of light, the point sources, they found like hundreds of thousands. Okay, we've got lots of correct answers, so I'll show the answer now. And a lot of you are correct. It's this tiny little thing here. So that's a slightly lower redshift 6.4. And so that's about 12.9 billion years ago. So it's taken the light 12.9 billion years to reach us, to reach our telescope. And so the sort of way to find these things, the sort of clue, is that they really do look like little red dots. So in a lot of the previous slides, whenever I had the phrase high redshift galaxy, I tried to put this sort of little red dot there, and that's very characteristic of images of high redshift galaxies. So even just in this first image alone, lots and lots of high redshift galaxies were identified. And so this was really, really incredible. This was a really, really breakthrough. But then that sort of started the redshift race. So not long after this image came out, many, many more deep images came out, and it seemed like the record for the highest redshift galaxy just kept being broken almost every week. So before JWST, the record was something like 11. A redshift of 11 was the highest redshift galaxy we'd observed, and then it went to 11.3 and then 11.9 and then 12 and then on and on and on. It just kept being, the record kept being broken by JWST. Until eventually we got to this. This is another beautiful mosaic image. This is taken from the JADES survey team. I'm not going to ask you guys to guess what JADES stands for because I don't remember myself. But this is the image of the good south field, it's called, and this is where the current highest redshift galaxy we've observed is located. And it's located roughly there. So it's, again, looks like a very, very little red dot, and it's at a redshift of 13.2. So this is only a few 100 million years after the Big Bang. So this was really, really, really groundbreaking, really. Yeah, currently that's the record holder for the highest redshift galaxy ever observed. But how exactly do we find and then estimate the redshift of these galaxies? So what the exercise we just did is kind of step one. So we'll take these images and we'll try to find these little red dots, although typically we'll ask a computer to try and do that, to find all the little red dots within an image. But what those images actually are that you see, those mosaics, they're actually stacks of multiple wavelength range images. So for example, this image, this highest redshift galaxy image, that's actually stacked together all of these different images in these different filters at different wavelengths. And so what we see is that in the shorter wavelengths, the kind of more bluer wavelengths, we don't see this galaxy at all. It's only in the redder wavelengths that we start to see a little point source at the center here of these circles. So to just show the wavelength range of these filters, so the first three are kind of these three, and then we're only seeing it sort of above 1.8 or 2 micrometers in wavelength. We're only seeing it in these sort of red-ended wavelength ranges. And so if we want to try and estimate their redshift, what we would do is we would work out exactly how much light we're getting from that galaxy in each of these image bands. So for the first 3 image bands, we're not really getting anything. We're basically consistent with 0 light from those galaxies. But then from the 4th image band onwards, that's when we start seeing the galaxy and we can start calculating how much light we're getting from that galaxy. And it's important to bear in mind that this is the wavelength cutoff for HST, so around 1.6 microns. So if it wasn't for JWST, we would probably have never found this galaxy, because at this lower wavelength, it's just simply, it's not there. It's completely dark. We don't see it. We only start to see it at these redder wavelengths. And so then the next step to try and estimate the redshift is we take what we consider to be kind of a model galaxy spectrum. So this is a kind of messy example, but the most important feature that we want to try and identify at high redshift is what we call the Lyman break. So this is where the galaxy flux is basically 0, and then it suddenly jumps and spikes up to a much higher value. And that happens at around a redshift of 0.09. And so what we will then say is if we ever see this jump at any redder wavelength, that must mean that there's been some redshift. So then we can calculate how much it's shifted and we can estimate the redshift. So that's kind of the process. You take the template, you see how much you have to shift it to match the data, and then you can estimate the redshift. So this template I've taken is not a very good match to this data, of course, but what the astronomers did for this galaxy was they found a much better template, and so they estimated a redshift of around 13. And then this was later confirmed with follow-up spectroscopy measurements for this galaxy. But I'm going to do a quick warning, which is that photometric redshifts we can get it wrong. And that's not, the astronomer's fault or the data's fault. That's just because you only get so much information. You really need spectroscopy to confirm the redshift. So these photometric redshifts, which are how the process I just described of how we estimate it, they are just estimates. We really need spectroscopy before we can confirm the redshift. And a good example of when this becomes an issue is there was a very convincing redshift 16 candidate identified within one of the latest JWST images. And not only did it seem to be redshift 16, but it also seemed to be very massive. It was very, very bright, and that would mean that it was very, very massive. And so being that at redshift 16, this is just about 250 million years after the Big Bang, we would have really struggled to explain how such a galaxy could exist with our current model of the universe. But thankfully, in this case, follow-up spectroscopy was obtained and revealed the truth. So what was actually happening was that this galaxy was actually a dusty lower redshift, so about redshift 5 galaxy that was just masquerading or pretending to be a high redshift galaxy. And the way it was doing that was because the dust within that galaxy was making it basically look like nothing was there at the bluer wavelengths. And then the emission lines were just in the perfect place to cause these flux spikes in the redder wavelength images. And that's what made us think that it was a redshift 16 candidate, but it was actually revealed to be redshift 4.9. So far that redshift 13.2 galaxy is still the highest redshift galaxy we've observed. But it's important to remember that all redshifts are really essentially unconfirmed before spectroscopy. In the interest of time, I'm gonna skip a couple of these slides, but I'm happy to go back to them at the end. But the main sort of takeaway from these is that JWST has really discovered a very surprising number of high redshift massive galaxy candidates, but they are still, a lot of them are still candidates at the minute. So JWST is, it's really brand new, and we're still learning how to handle the data. This is kind of what the data looks like when it's kind of raw, and we have to go through a very thorough cleaning process before we can make it look like those very pretty images that get published. And so there's still a lot of uncertainty in just how well we're cleaning the data. And also, like I said, a lot of these high redshift candidate galaxies haven't yet been spectroscopically confirmed. And so it's very possible that quite a lot of these could actually just be low redshift dusty intruders. So for example, this is a local dusty galaxy, and it does make it appear very red, much like how you would expect a high redshift galaxy to look overall very red. So all galaxies, high redshift galaxies, need to be spectroscopically confirmed, really, before we can say too much about just how many there are. So I'm going to very quickly give a quick summary of rebels. So like I said, the good thing with rebels is that these are massive galaxies that have already been spectroscopically confirmed with ALMA. So we don't need to go through that whole process of doing the photometry and then confirming the redshift. We already know the redshift, and we already know from ALMA a lot of information about the cold gas and about the dust. And so now with JWST, that's when we're getting more information on the warm gas and on the stellar populations. And what's also great about both ALMA and JWST is that instead of doing like the imaging and the spectroscopy where we get the spectrum separately, they both have capabilities to take both imaging and spectra simultaneously. So they're really, really powerful machines. So my two main projects is, first, I've been kind of focusing on the cold gas kinematics, so trying to understand how the gas is moving within these galaxies. And I'm doing that with ALMA. And then my second project is trying to investigate some of the warm gas properties with JWST. So going back to this picture of what we expect galaxies to look like at the high redshift universe. So in the low redshift universe, that's where we see galaxies like the Milky Way. Hopefully you can see this. It's just a little animation showing that. Oh, that's very loud. Milky Way-like galaxies are essentially thin disk galaxies that rotate kind of in the plane of your screen. But then at high redshift, we expect galaxies to be more dominated by very chaotic motions, simply because they've had less time to evolve into that sort of dynamically settled rotating state, and also because they're interacting with other galaxies a lot more, and that causes all sorts of chaotic motions. But what's interesting is one of the Rebels galaxies in particular has actually been found to very much look like a more local, well-behaved rotating disk. So if you imagine on this picture on the left, the red, this is an image of the cold gas within the galaxy, but the red gas, the red side of the galaxy is moving into your screen away from you, and the blue side is moving out of your screen towards you. So it's rotating in the plane of your screen. And this is how it compares to sort of a model prediction of what we would expect from a rotating galaxy. So it's a very good match, and it's very convincingly appears to be a well-behaved rotating disk just a few 100 million years after the Big Bang, which is really not quite what we were expecting. And a lot of other high redshift galaxies are shown to have chaotic motion. So this galaxy in particular does seem to be quite extraordinary. And then also quickly a sneak preview of some of the exciting JWST data. So like I said, we have information on the cold gas and the dust, and now with JWST, it does look like a blob, but bear in mind that this is data from light that's traveled 13 billion years to get to us. So the fact that we can detect it at all is still incredible. And so with this, we can compare how all these different components are distributed. And also, as I said, we simultaneously get the spectrum. And so what you're seeing in the spectrum is loads and loads of emission lines. And that means we can just do loads and loads of science. And so far, what we keep finding is that this galaxy and the other galaxy of the two that have so far been observed seem to be quite metal rich. So again, they seem to be very evolved systems. So the question that myself and most of the Rebels team are sort of focusing on is, how did such massive and evolved galaxies form so soon after the Big Bang? So I'm going to leave you with my summary slide. So just to remind you, if you want to stay up to date with some latest research, please have a look at AstroBytes. And if you're interested in learning more about massive high redshift galaxies, keep an eye out for Rebels. We expect the rest of our sample to be observed with JWST over the next year, but we'll be having papers coming out in the meantime. And as a reminder, like, JWST has not yet broken cosmology, and that's because JWST is still new, we're still learning about it, and we still need to confirm a lot of what we found. However, I will say that for the few confirmed high redshift massive galaxies, confirmed both with JWST and with ALMA, they do seem to be much more evolved than we predicted. So stay tuned for how this impacts our sort of picture of the evolution of the universe. And that is everything.